Hi everyone, so let's continue with unit 3 with electron affinity. Before we start, you will have to cross this out because this has just been copy pasted from ionization energy, and just rewrite the definition. So electron affinity is, we're actually going to add electron here. So affinity means liking, electron liking or electron addition. So when we are doing electron affinity, we are adding electrons to a neutral atom, and we're going to end up with a negatively charged particle. So let's see the definition and the equation. So make sure you note this down, make that correction in your in your copybook. Now this reaction is exothermic because here we have bonds that are being formed. So bond formation, you have the electron that is going to be added to the atom, so there's going to be some formation of bonds here, and because it is included, this is going to be exothermic. Now energy is going to be liberated, and you have a negatively charged particle that is produced. Be careful, both of them should be in the gaseous state. Values of electron affinity are provided in the section 8 of the data booklet, and here, as I mentioned, it's exothermic, energy is released, and the more negative the value, it is easier for the atom to accept an electron. And non-metals usually have high electronic affinity values because non-metals will generally accept electrons. So metals generally have a tendency to lose electron to have a stable electronic configuration, so Na will form Na+, but non-metals like Cl have a tendency to accept electrons to have the stable electronic configuration of noble gases. So it normally has a tendency to accept electrons, which means that it's easier for non-metals to accept an electron. So the more exothermic, the higher the value, the more negative the value, the easier it is for the atom to accept an electron. This is why non-metals usually have high electron affinity values, highly negative electron affinity values. So metals, they are kind of forced to accept the electron when we're talking about electron affinity. So here, whether it's metal or non-metal, when we're talking about electron affinity, means that we're forcing that atom to accept electron. So metals are kind of very afraid to accept electrons. This is why I have that picture here. While non-metals, for them it's very easy for them to accept electrons, because this is going to allow them to have the electron configuration of a noble gas. So very easy for them, and this is why it is going to have very highly negative electron affinity values. A positive electron affinity value shows that the anion is unstable and cannot be formed in the gaseous state. For example, for krypton, it's positive 41 kilojoules per mole, which means that Kr minus does not exist. So this is typical for halogens. For noble gases, because noble gases will not lose or gain electrons easily. It's going to be very unstable. So this is why it does not exist. Now, transient electron affinity. So across the period, as we're moving from group 1 to group 7, what will happen is that the electron affinity values is going to increase, and it becomes more negative. So when we're saying it becomes more negative, we're actually looking at the numbers. Just ignore the sign for now, just look at the numbers. If you look at the numbers, you see that the numbers is increasing. So the numerical value increases, which means that it becomes more exothermic and it becomes easier. Some exceptions occur, just like there are exceptions in ionization energy. And if you look down group 17, if you look at group 17 has the most negative electron affinity values. These values are the highest, and if you look at down the group, what happens is that as we're moving down the group, you know that the size of the atoms is going to increase, so it becomes bigger, which means that the nucleus is further away from the outermost shell. So when the atom is accepting the electron, so this is negatively charged, the nucleus is positively charged, so there's going to be a form of attraction between negative and positive. So this is why we say that it's exothermic, because there's going to be some form of electrostatic attraction, so bond formation. But as it gets bigger, what happens is that this gets further away from the so the nucleus gets further away from the outermost shell, so that it's going to become less easy for it to accept that electron. So when it's a small atom, so the electron is very close to the nucleus, so the attraction is more. So this is why down the group it becomes less negative, so the numerical value decreases. Why it decreases? Because it becomes harder for the atom, whether it's a metal or a non-metal, it becomes harder for the atom to accept electrons because the size of the atom is increasing. So even if you look at group 1, so as we go down the group, the size increases, so the electron affinity values become less negative, or the numerical value decreases. Same thing down all the groups. But of course there are some exceptions that we're not going to mention too much. You're just concerned with the general trend. Another term that we are going to look at is electronegativity, which is a measure of the attraction of an atom for a shared pair of electrons when it is covalently bonded to another atom. Now, let's say we have an OH bond. Now, in an OH bond, so O and H are covalently bonded, and covalently bonded O and H means, well, the oxygen will form another bond, but we are ignoring the other bond for now. Let's just look at this one covalent bond. So there is one shared pair of electron. So oxygen is more electronegative, which means that it has a tendency to attract that shared pair of electron closer to it, which means that in that bond, the shared pair of electrons is going to be closer to the oxygen compared to the hydrogen, which means that because of this, we are going to associate a delta minus to the oxygen and a delta plus to the hydrogen. So it kind of looks like the hydrogen is electron deficient and the oxygen has an excess of negative charge because all the electrons are attracted towards this atom here. So oxygen has a higher electronegativity than hydrogen, which means that it will pull electrons towards it, and if all electrons are pulled towards the oxygen, it gets a delta minus. This is what happens in the water molecule. So H2O, because oxygen is electronegative, the electrons are going to be closer. The shared pair of electron in that covalent bond is going to be concentrated around the oxygen. So you will have a delta minus around the oxygen and a delta plus around the hydrogen. So this is what electronegativity means. It's a measure of the attraction of an atom for a shared pair of electron, and electronegativity is measured on the Pauling scale from 0 to 4. So each atom is given a value for electronegativity, its ability to attract that shared pair of electron. And on that scale, fluorine is the most electronegative, element, which means that if you have, let's say, HCHF, fluorine is the most electronegative element, definitely delta minus here, delta plus here. If you have, let's say, CLF, definitely delta minus here, delta plus here, because this is more electronegative. The one that has the more electronegative is going to pull electrons from the shared pair of electrons, pull the electrons towards itself, and is going to develop a partial negative charge. You find the electronegativity values in section 8 of the data booklet, and what happens is that across the period, electronegativity increases. It increases because the atoms are getting smaller. So as it gets smaller, the effective nuclear charge increases, and it becomes easier for the nucleus to attract electrons towards it. So because it is very small, the nucleus is able to pull electrons from the shared pair of electron in that bond here, so it pulls it towards the fluorine. This is why it's highly electronegative. But if you look at down the group, the size of the atoms increase and the nucleus is shielded. There is shielding effect. Atomic radius increases. There is increasing shielding effect that predominates over nuclear charge, which means that the nucleus is less able to pull electrons towards itself. So this is about electronegativity. So if you look at the section 8 of the data booklet, you will see electron affinity over here. So electron affinity ranges from, you will see electronegativity values, and electronegativity values range from 0 to 4 on the Pauling scale. And see over here, so hydrogen is 2.2. So you see the values of electronegativity increase, and fluorine is the smallest atom actually. Because it's the smallest atom, is the one that has the highest electronegativity. And you see down the group it decreases, and you see all the values. So let's say you have a bond between silicon and, let's say, iodine. So if you compare the electronegativity values, silicon is 1.9 and iodine is 2.7. So because it has high electronegativity value, means that it's going to pull electrons towards itself. So this will be delta minus, and this one will be delta plus. This is what actually electronegativity values imply. So you're going to answer the basic questions on electronegativity and electron affinity.